Assalamualaikum warahmatullahi wabarakatuh. Good morning, Bapak Ibu sekalian, and good evening, Prof.Ben. Welcome to the last workshop. I think this will be the last and the latest workshop that already will have, and this is a big workshop. It's about predictive analytics and big data, and we welcome Pak Bill as a field director of Ready Project, and Pak.Ben Feng, Professor Ben Feng, who is the instructor for this online short course. And for us, for Ready Project, predictive analytics and big data is the 16th short course that we have conducted. With this, we met the target of all the planned short course that we are going to deliver, and thankfully with the new technology, online learning and so on, so we can organize this workshop, this short course via Zoom platform. And before we start the online short course, we have some information for all participants. Mbak Ernie, could you please start it? Yeah, especially for the participant, please name your display name with the format name and the institution, like a university or maybe from BPJS, P2 PK, and so on. And also, we request all participants to mute their microphone, so Pak.Ben can deliver all the session without any distraction, especially with audio distraction. And also, if you wish to have will engage during the session, please raise your hand, and then we can activate your microphone. And also at the end of the short course, in the fourth session, we will send you the survey for the evaluation of the workshop, so we can have what the good thing and what the thing that we need to improve in the future, hopefully, about how to manage the online short course. And next, yeah, and if participant, this is a new system for us. For those who wish to have asking question, please come to this slido.com, and with the code tagar short course 16, SC means short course, and then you can access you can put every question there. So we will manage the question that you raise in this platform to Pak.Ben. So with this, enable us to organize all your questions easily and more organized. And next, Mbak Ernie, thank you. And for participant, we will provide you with the certificates for the whole sessions, meaning you cannot take only one session. No, you have to follow all the 4 sessions. And also in each session minimum, you need to access 70 minutes. And also, we only provide for participants who are involved in Zoom platform. So for those who, unluckily, for those who accessing via YouTube, we cannot provide you with the certificates. Also, as this is the online short course, please all participants be responsible for the your accessibility, especially for the provision of internet, electricity, and the good ambience of your situation in following this short course. And the last one, I think, this is already mentioned earlier that we will have a survey, evaluative survey at the end of the session. That's information for all participants. And before starting the this workshop, I would like to invite Pak Bill Dugan. Oh no, your name is Bill Dugan, not Kinseng. Okay, I will invite Pak Bill as a field director of Rodi project to have a opening remark. Pak Bill, time is yours.
Okay, thank you, Pak Iksan. Selamat pagi, good morning to everyone. Can you hear me okay, Pak Iksan? Yes, good. Okay, super. Okay, usually I speak in Bahasa Indonesia, but I think today, because we've started off in English, and because Professor Ben Feng will be using English, of course, maybe I'll just speak mostly in English. So a warm good morning to everybody. I'm so happy that we have, how many people we have with us now? 86 participants, and the number keeps growing. And I know there's more people that are watching on YouTube and other platforms. So we're very pleased to see so many people joining for this important topic. And we're super happy that Professor Ben Feng was able to find the time to get the course organized and to give us his time over the next 4 sessions. This is actually the second time we've tried to deliver this short course. We were starting to plan it in October and November. We ran into some challenges and we thought we couldn't do it, but happily we found a way to do it, and Prof. Ben Feng was still available. So that's just great news. And as Pak Iksan said, this is the 16th short course. It's the last short course. So we're very happy that we can deliver this last short course. And it's fantastic to see the number of people. These online courses, we all miss the face-to-face interaction, but the great thing about online is that we can reach more people all over the country, and that's super. So we're very happy we can do it, and I'd like to thank Pak Iksan, Pak Ernie, Ibu Ivan, and all the Ready team in Jakarta for doing all the work to set up the course. I know it takes a lot of work to get everything all lined up and to work smoothly, and you've gotten to be very, very good at delivering these Zoom events. So well done to the team Ready, and thanks very much. So this is a very important topic, as Ben was saying just before we started. All over the world, we see that predictive analytics is a booming topic, and it's the same in Indonesia. We know how important big data is and analytics, not just in the insurance industry and pensions and that, but also in e-commerce and all kinds of. Indonesia, of course, has a number of very successful digital companies and decacorns like Bukalapak, Tokopedia, Gojek, and many others. And of course, they all rely very heavily on predictive analytics and using data. Sometimes people ask us, they say, well, what's going to happen to our actuaries? Still going to be needed because now we have artificial intelligence and we have machine learning. Maybe industry's not going to need actuaries anymore. But I've talked about this a lot with Prof. Ken Seng and other people. And if we look back in history, in the 1960s, suddenly calculators were available. And people thought, oh, that's going to kill a lot of actuarial science. But it didn't, of course. It just allowed actuaries to do more things faster. And then in the 80s, computers became available and affordable. And people thought again, oh, people are going to use all this computer power and software, Profit, and so many other different actuarial softwares. But still, we see there's a need for actuaries and a greater need for actuaries all the time. We know that Intact, one of the Canadian general insurance companies, when we visited them a couple of years ago, they have 50 actuaries just working on big data. So it just shows how important it is. So this is really a very important topic now, for sure. Artificial intelligence, machine learning is going to play more and more of a role, but there's always going to be a need, I think, for good analytical skills and for expert judgment to say, what does the data ultimately mean and what should we do with it? And not all actuary science graduates in Indonesia or everywhere else are necessarily going to work in, kind of the big 2 or 3 sectors, that being insurance, and pension management, and maybe investment financial management. Lots are going to start working in all these high-tech companies, e-commerce companies, and other companies that are using big data. So having skills and knowledge in predictive analytics will be really important and really, really useful. So we're really happy, as I said. Thanks again to Prof.Ben Feng. I hope you'll all enjoy this course. As Iksan said, please stay with it for all 4 sessions. Okay, and I believe we may have a 5th session. We're trying to set up a 5th session with someone from industry. So please join everything as much as you can so that you can get the full benefit. So thanks again to everybody, and Prof.Ben Feng and everybody else. I wish you a successful and an enjoyable course. Thank you. Terima kasih.
Thank you.
Yeah. Thank you, Pak Bill, for your opening remark. Yes, we are in preparation for the 5th session, especially for the big data application in Indonesia. But at the moment, we haven't released the information yet because we haven't found the instructor yet. Okay, that will be next round of the short course. And okay, let's start the short course to Pak Ben. And for your information, Pak Ben is, I think the majority of participants knows Pak Ken Seng Tan and Pak Ben and Pak Ken. Ben and Ken is very closely related academically. So I think Pak Ben will explain himself, introduce himself, who you are, Pak Ben. And from now on, I will hand over all the session to Pak Ben. And ladies and gentlemen, Bapak and Ibu, please welcome Pak Ben. Pak Ben, time is yours. Thank you.
Thank you. Thank you for the great introduction, and thanks for the whole team behind the scene working so hard to get this course organized and finally set it up so well. And it's a great pleasure and honor and privilege to be able to deliver this course. And I hope this course has something to offer to every participant, regardless of your background. And hopefully you'll become a better actuary after this course. And as Bill said it very well at the beginning, that there's always a need for actuary, and actuary is not only defined by knowing statistics like life table and the mathematics behind, but also actuaries are defined by continued improvement of their skill set. If the environment change, then we will adapt to the environment. So being able to adapt to new environment and evolve with the environment and leading the evolution of the environment is also part of the actuarial genes that we all share. Okay, so I'm going to share my screen to start my presentation. Iksan, can you give me a thumb up if you see my screen? Can you see the screen? Okay, thank you. So data science and predictive analytics is a huge field, and I'm trying to shrink it down to the most relevant part for actuaries. And by actuaries, I don't mean just actuaries in insurance company, but also serving in the financial industry as well. So in this first session, I will give some examples, mostly going through motivating examples for how insurance and finance have been impacted or actually revolutionized by big data and predictive analytics. Before I start the course, however, I want to give a self-introduction so that you get a little bit closer to everybody and so introduce myself so everyone knows about me a little bit more. My name is Ben Feng. I did my undergraduate and master in actuarial science in Waterloo. And as Peg accent kind of hinted on, during my master's study at Waterloo, Ken Tseng was my master's supervisor. So in some sense, he is my academic father. And a lot of what I'm doing in research can be traced back to the time when I started my first research project with Ken Tseng. So I owe him a lot. And my PhD is actually in financial engineering. So switching from math to engineering to explore a little bit more out of curiosity. And after I got my PhD, I came back to Waterloo and started teaching actuarial science again, but with a bit more focus on the scientific computing / machine learning side because of the engineering training that I had in the PhD study. And my research interests include financial engineering, machine learning / nonlinear optimization, really, the algorithmic design, how to solve machine learning problem more efficiently. And also Monte Carlo simulation, that is the stochastic simulation that we kind of do either before or after the training of a machine learning algorithm. So that's about me, and you will see a lot of my, well, you see some of my research interests kind of flowing in or sneaking into different parts of the lectures. So when it's time, I'm going to show you what part relates more to the financial engineering, what part relates more to the machine learning, right? And for this course, so not only today's lecture, but 4 sessions in total, what I had in mind is actually giving you the hands-on skill that you could actually take out of the box and start working on real problems. So it's very light on mathematics, derivation, and proof. That's not what I had in mind. It's more on computing, a little bit on the programming side to show you the actual skill that you actually need to jump into a real problem in practice. Of course, there will be a little bit of background that we need to know, not only knowing the machine learning and statistical learning techniques, but actually need to know how and when to apply them, and more importantly, when we should not use machine learning and statistical learning. Okay, machine learning has become so popular and so hot in the industry. People kind of just throw machine learning algorithm at every single problem that they see, and in my opinion, that's kind of a mistake. So it's important for us, the actuaries, to actually identify limitations of machine learning algorithms as well, and knowing the limitation helps us a lot in understanding the importance of context and the background of a real problem, rather than just jump into the problem directly without much understanding. And when I'm describing this course, so the title of this short course is Predictive Analytics and Big Data. So even though the focus is on computing and a little bit on the programming side, during my description or during my lecture, I will encourage everybody to pay attention to the data that's being used. In a course like this, the data I'm using is out there, meaning it's kind of publicly available and people have cleaned the data, and it's small enough toy example so that we could give demonstration in lectures like this. But there will be a time when I ask you to pay attention to data, to extrapolate what we learned in this course to real applications where the data is much, much less structured, and you might need a lot of time just dealing with data, cleaning them, collecting data, before you can actually run any kind of machine learning algorithm onto the data. So working with the data itself is a big part of real applications, but it's not focused in this class. From time to time, however, I do want to stress the importance of getting and manipulating data. So that will be part of the description in the course, but not really the focus. The focus really is on the algorithmic side. What kind of machine learning algorithm, and then when should you use it? Okay. A couple of online resources with the generosity of a lot of authors. Nowadays, many authors would provide free copies of their book online. And some publishers as well, during this pandemic, they're willing to share the resources that they have. So I'm providing a couple of textbooks. All of them are free online. The links are provided in the slide. So you could follow the links to get all these online resources. And there are many, many more. And these 3 textbooks are mainly the sources that I use to develop this series of lectures. And as I repeated again and again, that computing is a big part of this course. And to give everybody hands-on experience, at least working with some toy example with practical flavor. So you are highly encouraged to bring a laptop, a PC or a Mac, what have you, with R and R Studio installed. So I would assume that everybody has some basic level of some basic working knowledge with R and R Studio. At the end of today's lecture, I will give somewhat high-level introduction to R and R Studio, and we will start from there. Data science, it's important to kind of see what it is and what it does. There are many, many different textbooks and online resources. Everybody has its own, his or her definition of what data science is. I will give my own definition, well, not mine, but my understanding of what data science is, and then what are the different views or subfields of data science. Data science, in my mind, is an interdisciplinary field on the method of extracting knowledge from data in different forms. Okay, so this is kind of vague, right? At face value, there's no mathematics defined. There's not even the word algorithm in it. So it's a general form, general way of extracting knowledge somehow, one way or the other. And there are many subcategories in data science. For example, databases. By this, I mean constructing a database for a company. What kind of database should you build your data on? So the engineering behind building a database for different types of company, well, it used to be ad hoc. And through time and experiences, different industry kind of get a hang of it. But nowadays, the challenge is there is too much data. So the traditional way of storing data may be inefficient and insufficient. So people need to change. And what kind of changes is needed? Well, it depends on the database engineering skill. And that is part of data science. Data mining at a high level basically means how you collect your data. We statisticians and actuaries tend to think about data as matrix or data frames, if you know R well enough. But that's not all, right? Data takes so many different forms nowadays. For example, videos could be one form of data, and picture would be one form of data. And those are pretty difficult to put into matrix form. Okay, so data mining, how you store your data after mining it, well, that is also part of data science. Data visualization, for a long time, at least in my time as a student, I didn't pay too much attention to it. I did not think that's important because I thought it's not a quantitative category of statistics. You just have a couple of plots like QQ plots, scatter plot, line plots, what have you. So visualizing data doesn't seem to be a big thing a decade ago. But now, my appreciation for data visualization has increased dramatically. When you have a huge data set, a data set so large that you just couldn't make sense of it if you don't know how to see it. If you don't find the right angle to see a huge data set, the data wouldn't make any sense whatsoever at all, let alone start doing any kind of meaningful analysis on it. Okay, so data visualization, the tools to visualize data, and developing such tools and knowing how to use these tools has become such an important part of a day-to-day job for a data scientist. Okay, so even though I'm talking big on the first three items, those three I'm going to shrug my shoulder off and say, well, those three are not going to be the focus of this course. In this course, I'm going to focus on different machine learning algorithms and different statistical learning algorithms. So the statistical way or mathematical ways to analyze data, that's the focus of this course. Okay, but I don't want you to underestimate the importance of the other three. Okay. Next up on predictive analytics and big data. Okay, so these words, in my own opinion, has been used too often. Okay, so any kind of analysis or a moderate-sized data set, in some occasion or scenario, people might say that predictive analytics and big data. Okay, and they are very important. They have significant impact in finance and actuarial sectors. And that will be the focus of this course. I'm going to show you examples on that. And it's no longer an exaggeration to say that big data and predictive analytics has already become part of these sectors. So it's no longer a separate new skill set. This skill set, data science skill set, predictive analytics skill set, has become necessary for an actuary to survive in a financial and actuarial sector. So this gives rise to new terminologies. We all like new terms and fancy terms. So you might see in the news, FinTech and InsurTech. And these are acronyms for financial technology and insurance technology. I will show you a couple of FinTech and InsurTech examples and clarify that, yeah, the use of big data and predictive analytics actually give rise to new applications in finance and insurance, or at least new techniques to solve traditional finance and insurance problems. And that will be the next part of my presentation. So let me start with some typical tasks in the finance sector, asset management, or in some sense, portfolio optimization. So asset management in a very vague way can be think of, you want to have some advice in, say, what stock you want to purchase, what kind of asset you want to have. So you might be thinking on a personal level, what kind of investment you want to have. But asset management, what I'm alluding to is actually managing the asset, not for a person, but for an insurance company or a bank or any other financial institution. Okay, so I'm hinting on the asset management on a corporate level, right? And that is a very important task, whether traditionally or nowadays. Okay? For insurance company, whether you are able to invest your asset well has a huge impact on the profitability of the company. Traditionally, you will have some fund manager or asset manager with years and years, decades and decades of experience, and then and use that experience to manage the company's asset. Okay, so it has worked quite well for decades, in my opinion. However, with the help of big data, or with the help of predictive analytics, nowadays we can build asset models from huge amount of data. The amount so huge that no asset manager could ever been able to look at all the data. Okay, and in that sense, the asset model built from this massive amount of data, if you believe in machine learning, and if you believe machine can actually learn from data, then its knowledge, the knowledge learned by this asset model could be much, much better than the decades of experience of a star asset manager. And this gives rise to something called automated trading. Okay, so instead of having a manager telling you when to trade any kind of asset, the algorithm that takes in massive amount of data, some kind of analysis, and give you advice in what kind of trading you need to do in the next month or next 6 months or next year. And the reason for automated trading, rather than having fund manager to do this task, is to get rid of the human bias. Okay? So as humans, we all have personal preferences and have all kinds of biases, and these biases could affect our decision making. So with a machine that doesn't have any emotion, then we can have more scientific and objective asset management. Okay, and that also that is also related to a different application in the finance sector, and this is more related to day-to-day business on a personal level. I'm not sure how many of you have actually been to the bank and start asking financial advisors for their financial advice about what stock you should buy and what's the proportion of wealth you should put in stock versus bonds or versus cash, or maybe purchasing a house and take out a mortgage. So financial advisors are very, very common in our day-to-day life. And now, with the help of predictive analytics, something called robo-advisor has become quite prevalent. So you can now give some of your personal information, for example, your monthly salary, your age, and your profession, and your some kind of risk assessment question about how much risk you could take. When a robo-advisor has taken your personal information and combined that with the massive amount of data behind the scene that he has done analysis on, it can give you advice that no human financial advisor could give, because robo-advisors have used so much data back in history, so huge amount of data in time dimension, but also huge amount of data in the space dimension. Robo-advisor may suggest you to invest globally in different countries for different reasons. For example, robo-advisor can take taxation into consideration for your investment. It can take into different policies in different countries into consideration. So that if you want to have an equivalent quality of financial advice, you will need to have a star team of lawyers, a star team of accountants, and a star team of financial advisors. And these three teams collaboratively give you financial advice. Instead, robo-advisor can fit into your personal laptop. Okay, so again, the reason of us wanting to use algorithms and computer to give us this advice is for us to receive more scientific and more objective asset management advice. Credit risk assessment. Some of you know it, some of you don't. For commercial banks, a lot of business come from lending out money or giving out mortgages or giving out business loans. So it's very important for the banks or for other types of lenders to tell whether a particular borrower will repay the debt. Okay? And that in financial terminology is called credit risk assessment. Okay? So credit risk assessment in the past could be a very time-consuming process. The bank, when you take out a loan or a mortgage from the bank, the bank may check your credit report. In some cases, the bank may call a couple of people around you, the references, and then some human judgment behind the scene as well to tell, well, whether this borrower has good credit or not. But, but with the help of predictive analytics, we can actually give very timely and credible credit risk assessment to tell if a person is going to repay the debt in a timely manner. Okay? And this evaluation, because the model takes in so much data and the analysis is so rigid, this evaluation could be very, very precise. So much so, it can assign a probability of this person repaying the debt on time. And I've seen some algorithm that could actually predict when will be the likely time for default if default happens. So in these cases, there's some numerical data, for example, credit score, for example, how long have you had your first credit card, and what's your bank account balances. So those are typical numbers, numeric values. But there are also something else that could fit into this kind of risk assessment algorithm. For example, typing speeds. If you're filling your own mortgage application using an online interface, the speed that you type in and the words that you have, the words that you use in your application, all of these can be factored in. And this kind of behavioral data is new, right? Typical or classical credit risk assessment doesn't take into account of your personal characteristics in the past. But now, with the help of big data, the credit score or credit risk assessment algorithm could take in all kinds of non-traditional type of data. With globalization, fraud detection and fraud prevention has become such a big. Sorry, I was just checking if anyone raised a question. Fraud detection and fraud prevention is also a huge part of global banks, right? Banks that operate globally, because it's important for them to detect fraud and even better, to prevent fraud from happening. And in the past, this task exists in the past. For example, in my personal experience, there was a time in my life, or even nowadays, I constantly travel between US, Canada, and China. So when I fly from one side of the globe to the other side of the globe, sometimes my credit card got deactivated without my knowledge. And that is because behind the scene, the credit card company thinks that I lost my card and somebody else is using my card on the other side of the globe. Okay, so that is kind of a typical scenario for fraud detection and fraud prevention, at least in the past. Nowadays, with globalization, there are so many people just like me that would travel globally and frequently. So those type of classical algorithm trying to identify fraudulent transactions based on geolocations doesn't work quite well anymore. So they need new algorithms and new developments in the algorithms in order to tell whether you are using a typical transaction that you usually use. I'm using those words typical and usually in a loose sense because the typical could be different for different people. So the ability to monitor transactions in real time. So this is not a classic matrix form of data. This is an online data that comes in real time, or sometimes we call that data stream. The ability to monitor transactions in real time and developing algorithms to analyze data stream will help us or help the credit card company or help the bank to flag the fraudulent transaction or to at least identify some transaction that could potentially or with a high potential to be fraudulent. And they would want to identify fraudulent transactions that fall outside of the quote unquote average norm. And this kind of average norm, as I said, is different for different people. So you need to have a huge amount of data to identify what is the average norm for each customer. And that has to, and that part of the algorithm use behavioral data or sometimes use social media data as well. So if you've been purchasing a lot of sportswear, basketball, football, hockey, what have you, and all of a sudden your purchasing behavior change and start purchasing perfumes and start purchasing lipsticks. I don't know, I'm making these things up. The credit card company may flag initially that you are purchasing outside the average norm until they track that there is another behavioral data that they can track and start identifying, well, you are not actually changing your behavioral data. What really happened is because you just got married and you start purchasing gifts for your wife. Okay, so this kind of behavioral data as well as social life data now is also being used, subject to some personal privacy rules, of course. And this is, I won't say an entirely new industry, but in the past, this is not a separate industry. Fraud detection and fraud prevention used to be a subpart of most banks. But nowadays, there are FinTech companies whose main goal is to provide fraud prevention services to other firms. So the predictive analytics algorithm has become so advanced that some firms would be able to just leave on the fraud protection. So the fraud protection and prevention could be separate from a particular bank, and these firms could provide services to all different banks. Another example is determining lifetime customer value. And this has a lot to do not only inside the financial and actuarial sector, but targeted marketing as a whole. What this is, let me speak in the language of FinTech. Instead of treating customer coming to the branch of a bank as a one-time transaction, which is the case in the past, nowadays, FinTech companies wants to know when you come into the bank and when the bank knows a little bit more about this customer, the bank wants to estimate what's the entire potential lifetime volume or value of this person would have if the bank start developing a long-term relationship with this customer. And this is important for banks because then the bank could start advertising or promoting products to customers that they think would most likely to have high lifetime value. And so this creates the opportunity for upselling, meaning charge a little bit more fees, and targeted advertising, meaning you target your advertisement to specific group or subpopulation so that the bang for the buck, if you will be high. Many pre-approved credit card, and these 2 bullet points are actually coming from my personal experience. After having a salary direct deposit into my bank, that was like 4 or 5 years ago when I started having my first job, right? I went to a bank and then set up a direct deposit so that my salary would be deposited directly into the bank, into my bank account. And after that, I start receiving a lot, literally a lot, pre-approved credit cards. And this is from the customer side, seeing in real time the targeted marketing. The bank knows that, well, this guy starts to have the first job and probably his spending behavior will change, and now is the right time to sell him credit cards. Okay, so that's one aspect. Another one is when I start to have some savings in my saving account, and then I'm not investing in the stock market or anything, just let the money sit there, I would constantly receive calls from financial advisors and start asking, what am I going to do with that saving account? What's the plan for those money? Do I want to invest those money in some equity market or some other kinds of investment? Or do I want to use that money to start purchasing life insurance? So with a little bit of personal data, well, in this case, amount of money in my savings account, with very little data, the bank could actually advertise very effectively. They could identify the subgroup of population who would most likely take their products. And again, nowadays, this business has changed a little bit. Data such as social media feeds and direct feedbacks by survey can both be used to build a lifetime value model. This last part is kind of a general description. The example I give is less specific, but I know they exist. So data science, this is more about data mining. What kind of data can you actually collect and start analyzing? So it allows a customer's payment and purchase history, however long that may be assessed at a very, very granular level. There is a timestamp, there is the amount that you spent, there might be a currency on the amount that you spent, and then there is a geolocation about where you spend that money. So then using this very, very granular data, it helps different companies to predict what your next purchase might be, what kind of products that you are actually interested. And instead of acting on this data themselves, so the credit card company owns this data, but the credit card company doesn't actually sell products. So what can they do? They can see the data that they have is the product that they have. So credit card company, I'm just making this up because I didn't see this in first person, but I'm guessing credit card company or some banks could actually sell their data to manufacturers and to different online sellers like Amazon, right? Amazon would pretty much like to predict what you're going to buy next and start giving you promotions and start giving you advertisements on the products that you're most likely to buy so that, well, to make the last push for you to purchase products from their website. And this evaluation typically in the past would use basic analytical score built on month-to-month volume of spending. So this volume of spending basically just tells whether you have some extra money to spend. But nowadays, the granular level of data could go so far as not only telling whether you have extra money to spend, it can also predict what you want to do with this money. Okay? If your browser history has been searching for basketball for a while, then you're going to realize when you go to some other website has nothing to do with basketball, you are going to see advertisements about basketball, right? So this is your browser, whichever brand that you're using, your browser is actually selling data to the advertising company. This is useful for targeted advertising and loyalty rewards and other forms of active customer interfacing. Okay. So that would be a couple of examples that I either have firsthand experience with, I have seen, and then also this last one, kind of anecdotally, I could imagine this application exists. So coming back to the FinTech area, okay? So just a quick summary about all the examples that we have seen. There are three main FinTech areas where technology is the main driver in transforming the financial services that's being provided nowadays. The first one, with no doubt, the lending and banking services. The huge growth of P2P lending has come out of the ability to analyze so much and so granular level of data. Credit risk assessment has become so quick and so accurate that the banks are able to identify some subpopulation that they would otherwise not lend money to. But nowadays, because the predictions are so accurate, they can charge a slightly higher interest to the group of clients that they think is only slightly more risky than the other group of borrowers. So clearing, I don't have concrete examples on this side, but after reading some books on it, I believe this is also important. Blockchain is a hot word nowadays. So whenever I talk about blockchains, people immediately think about Bitcoin, but not necessarily. Blockchain is just a technology, or in some sense, a particular type of recording some transactions. So this technology could be applied in different areas, not just as Bitcoins. Trading, algo trading is a technical jargon, meaning you have ultra high frequency trading, and the trading is done by algorithm that you set up. And the ability to use algo trading, in the past, it could be just some basic rules, for example, setting the higher and lower limit to buy and sell particular stock. But now you could actually tie your algorithm with a lot of other data. And by data, I don't just mean numerical data like volume and price. I also mean other data like the balance sheet, or the competitor information, or sometimes just the news cycle data. I have seen research on analyzing the correlation of tweets on certain company and the effect on their stock prices. And some of those studies actually found correlation between the trends on Twitter as well as the stock price changes over time. So there is something to be learned in that domain. So I hope that's enough example to motivate you to appreciate the power of data science. And it's not at all an exaggeration to say data science has revolutionized the business and financial world. Okay, so the amount of data, the granular level of data, and the continuous data stream, all of this has contributed and contributed to this change. Okay, and of course, in the meantime, because of the size and the volume of the data and different types of data, the database engineering, the data visualization has all become essential skill sets. Now let me talk a little bit about the specific machine learning and statistical learning, right? Instead of talking big and fancy terminologies, I want to get down to earth now and start defining some of the terms I'm going to use repeatedly in this series of course. So machine learning and statistical learning, in my mind, they're still different, but nowadays they have become kind of the same thing. They're both important subset of data science. They are very similar as they both study the design of algorithms that can learn from data. And we all believe that with the large amount of data, feeding data into machine learning algorithms will improve the learning. And eventually the task become automated. So the goal of using machine learning, the goal of using statistical learning, or the goal of using predictive analytics in general is to reduce and eventually get rid of the human interference in whatever activity that you're doing. For example, in the robo-advisor, rather than having a human to give financial advices to different people, at the end of the day, we want to have a smart enough robot to give scientific and objective financial advice. But there are also some differences, at least in the past, right? Machine learning really arises from AI, artificial intelligence, in the computer science community. So they focus more on the large scale application and prediction accuracy, and with a lot more focus on the computation side rather than the modeling side. Statistical learning, on the other hand, arises from statistics. So it emphasizes more on models and then how to interpret the model. So it's important for a model to be understood by users. And so the precision and uncertainty, how to model this uncertainty was, at least in the past, a focus of statistical learning. But again, nowadays, the distinction between these two has become blurred over time. And under the current environment, machine learning is certainly a much, much bigger buzzword in application. And here is a kind of high-level picture about how machine learning is actually used in practice. In my mind, it's being used in a cyclical pattern. You have predictive analysis, which forecasts and diagnoses and scale up the analysis. And with the predictive analytics, or with the prediction given by the first step, then you start prescribing some kind of solution or some kind of actionable items and provide those items to the management. And then the prescriptive analysis try to give some optimal solution, try to give advice in the decision-making process, and then all of this goes into the management, and the management will start thinking about the operational side, meaning how do we actually take the advice and then transform those advice into actions. And then part of that management also, usually towards the end of a particular task, they will observe, measure, and collect data for the next cycle. And descriptive analysis is more about data visualization in my mind. Just have a preliminary understanding to detect some interesting pattern in the data, try to give a first account explanation for the data, and just a coarse understanding. And with that coarse understanding will lead to the next cycle for predictive analysis. So this is the typical cycle in a real application for data science. The different types of machine learning problems, I don't think there's any debate on this one about what the different categories are. Okay? Typically, it's categorized into supervised learning and unsupervised learning. And sometimes in some textbooks I have seen, supervised learning is being put into the predictive analytics, and unsupervised learning is being put equivalent to the descriptive analytics. It's not necessarily a convention I would adopt, but there are textbooks that makes this distinction. It's a lot easier to distinguish supervised learning and unsupervised learning with some notation. So let me do just that. Given a data set, and by data set, I want everyone to think about, say, a simplest linear regression that you have in mind. You have some X as the regressors or the predictors, and you have the corresponding Y's, which is the prediction or the response. So a typical task in supervised learning, which is the task in linear regression, is to build a model to predict Y from some X. And Y star and X star, and the X star in particular could be some X that's not even in your original data set. In many machine learning applications, the typical jargon for X and Y are feature and label. Okay. In linear regression or simple linear regression, X is called a regressor, Y is called a response. But in machine learning, X is called a feature, Y is called a label. If Y is continuous, then this is usually called a regression problem. So typical continuous label includes stock prices or the survival time of a particular annuitant. If Y is discrete or symbolic, then this is called a classification problem, which will be the focus for us in the next class. And this is very useful in practice as well, because, for example, you want to have a classification problem to label the spam email versus the important email that you really want to read. Unsupervised learning, on the other hand, does not have the labels. It's only giving you the features. Okay, so this is kind of typical in the sense that sometimes you just don't know the result of something, but you have a huge collection of data. Okay, so for example, in an insurance company, you might have some data for whether a insured is male, female, smoker or not, and the age. And with all of that, you don't have the label or the death status of that person. And X can be high dimension or unstructured. For example, you might have X as just a picture, and you want to ask the algorithm whether a cat is in the picture or a bike is in the picture. This is called unsupervised learning because there's no label. So all you can do is to observe the X characteristics and start grouping them into different groups and start thinking about why are they grouped in a particular way? Are you observing some specific patterns after you group the data together? A couple of examples, 2 examples of each type. Based on the characteristics of a past credit applicant, right? A lot of them. And in the past, some credit applicants repay their debt, some of them don't, some of them just default. With those data, with both characteristics as X and repayment history as Y, you could predict how likely a new applicant is to repay a loan. Or in an actuarial application, given the characteristics of past insured and their age of death, then you could predict the age of death for a new insurance applicant. Unsupervised learning. So if you are Amazon, for example, and you have the purchasing history or some kind of credit card information for different people, you might want to group different customers or cluster the customers into groups with similar spending habits. So you could start sending out advertisements in groups. And another application would be learning association rules from data. All you have is the past history of who have applied for mortgage. And you could start learning rules about, say, somebody who recently got promoted and had a baby were more likely to get a mortgage. And then you could start sending out mortgage promotions to this subpopulation. So with those in mind, let me just spend the last couple of slides explaining the central theme of this course. Some of these themes we have time to dive into, but some of these themes we don't. I still want to get that knowledge across in the theme of this short course. So, just a big picture. When we are talking about predictive analytics, at least with the focus of this course, what are we really trying to do? So this data set, I sent that out to all the participants. It's a public data set available in R. It's an advertisement data set. When I dig into a little bit, this data set is not quote unquote real, it's actually simulated. It's actually a data set with 4 columns. So the data set is laid out in a matrix form with 4 columns. So there is the first 3 columns are the amount that a company put into advertising in TV, radio, or newspaper. And the last column gives the labels Y, which indicates the sales in 1,000 of units. So it's basically saying by spending certain amount of money in different channels of advertisement, how does it affect the sales of whatever product this company is selling? So when we talk about predictive analytics, what we are trying to do is we want to predict the sales as a function of TV, radio, and newspaper advertising budgets. So we want to find such a function so that when we put into new TV, radio, and newspaper budgets, we can accurately predict the level of sales. Okay? And a good predictor is our final goal. And as always, with mathematicians and statisticians, we always like to ask the question of, can you define what you mean by good? And that is by no means an easy question. In fact, it's a very difficult question to answer. So I'm going to propose four different criteria for what it means to be a good predictor. The first one is generalizability, which means we want to construct predictors that generalize well to unseen data. If some of you are making notes, then you want to note the word unseen, right? Are you able to use the predictor to make predictions for some data that we've never seen before? Okay, so predictive analytics, at the end of the day, we want to make predictions. We want to know how good the prediction is, rather than predicting the past. The past has already happened. We want to make predictions on something we have not seen before. And this is no easy task. I mean, finding a predictor that's generalizable is not easy at all, because it requires capturing the useful trends or other characteristics in the data. This means we should not underfit the model, which is the first graph here. But at the same time, we want the predictor to ignore any meaningless random fluctuations. The picture on the right clearly overfit, and we want to avoid that as well. Okay? And just as a side joke, we keep emphasizing generalizability as if we want to extrapolate our prediction, or we want to apply the prediction into unseen data. Something we want to be cautious about is to avoid unjustifiably extrapolating beyond the scope of given data, right? So extrapolation is dangerous. So we want to make prediction, but still within a reasonable region of extrapolation, okay? And the picture at the lower corner is really an exaggeration about what unjustifiably extrapolation means. And theme number 2 is the so-called bias and variance trade-off. And this is the theme I'm going to dive into in the third lecture. This is something you really need to understand, and this is probably the most mathematical part of this course. We're going to have some mathematical discussion in the third lecture of this series. The prediction error is something we want to minimize, right? A good predictor should have small prediction error. Yes, so that's our consensus. Mathematically, what we can show is that the prediction error contains 3 parts, 2 of which we could actually control. The last part, unexplained noise, by nature, well, we cannot do anything with that. It's just random noise. We have no way of dealing with that. But by constructing different types or different kinds of predictor, we could control the variance and the bias of our prediction. In the same language as theme number 1, the picture on the left have high bias and low variance. Low variance because the model is so simple, so your model doesn't fluctuate too much. But it has a high bias because your model is so different from the pattern in the underlying data. Picture on the right has low bias because your prediction will fit your data pretty well, but it has a huge variance in the prediction. And I'm going to leave it like that for now. We're going to revisit this theme in lecture number 3. Theme number 3 is about the model itself. Okay? So on the graph on the right shows a couple of different algorithms, machine learning algorithms, and plot them with flexibility on the x-axis and interpretability on the y-axis. Flexibility, for some of you, if you're confused about what this means, you could translate this somewhat informally as complexity of your model. Not exactly, but you could make an informal translation like that. So when your model becomes highly complex, then probably your model is not very interpretable. Okay, simple models are very interpretable, but it's not very flexible. The model is so simple. And this sounds like a trade-off to you, then you're on the right track. Some models are highly structured and interpretable. Some are highly flexible but less interpretable. And the trade-off kind of shows in the picture. The best predictor, this is the ironic part when you jump into a practical application. The best predictor may turn out to be an uninterpretable and hard to interpret black box, meaning a complex, complicated black box model makes the most accurate prediction. However, the question for you, the data scientist, is whether you really just want to have an accurate prediction without really knowing why the prediction is accurate. And there are plenty of reasons the answer is no. Okay. In practice, there are practical perspectives that you really want to cope with. Sometimes you may prefer, or your user may prefer, a more interpretable, understandable, but slightly worse performing model than a black box. For example, if you're explaining your model to your investors, or if you are explaining your model to less technical audience for regulatory purpose, you don't think lawmakers are all mathematicians, right? So if you're trying to sell your modeling to regulators, then you probably want to tune down a little bit and choose a model that the regulators can actually understand. The last one is something I want to mention at least once. It's super important in practice, but with only 4 lectures, I do not have time to go into. With a little bit of extra exaggeration, if you are given a limited amount of data, then any sufficiently flexible model can learn nearly any complex pattern and structure. Okay? So with unlimited data, you could kind of do anything. But in reality, we have only limited data and often many variables. Okay? And not all of these data is useful. Okay? Not all the variables are useful, and you have to select the data, or sometimes you need to transform the data a little bit before putting them into a linear regression model. Okay, you might want to take logs, you might want to standardize your variables. Identifying useful variables and sometimes combining them, transforming them into useful forms takes experience. Okay, it's not something a math teacher can tell you exactly what you need to do in every single circumstances. It's just not possible. Okay? So feature engineering refers to precisely how you actually transform the data before putting the data into a machine learning algorithm. Okay, so to close this theme, I want to give you 2 quotes. Feature engineering is the process of transforming raw data into features that better represent the underlying problem to the predictive model, resulting in improved model accuracy to unseen data. Okay, so this is precisely the importance of feature engineering. Sometimes it's not about the algorithm that you're using, it's about the usefulness of the data that you are feeding into the algorithm. Another quote, some machine learning projects succeed and some fail. What makes the difference? Easily the most important factor is the features used. Okay, so you may have the silver bullet right in front of you, but you may not have the right gun. Okay, so the algorithms, yes, they are important, but feature engineering is also something super important as well, because that would determine how accurate your model prediction is. Okay, so with that, I only have one thing left. I have an illustrative example in R and R Markdown, which is in the R file that I distributed before the lecture. Okay, so let me stop sharing the slides and start sharing the R Markdown. Okay, so this is the final product of the R Markdown file that I sent out. Okay, so I'm going to show you the code and run through the code in a minute, but now let's take a look at the final product. So this is a HTML file, which means you open the file with a browser. And if you scroll down this page, it feels and it looks exactly like a web page with titles and with some descriptions, as well as some R codes. More importantly, it looks like the R codes are actually functional. So the R codes, it looks like the R codes is being run in the website. Okay, and that's the benefit of R Markdown, because you could have the code running, and whoever takes this code could reproduce exactly what you did in your program. So there's no ambiguity when people communicate the same set of code. And in addition, you could organize the narrative or the plain text to explain what the code does and what is intended to mean. Okay? And then you could have sectioning, and you could have table of content to directly jump to different sections. So to me, this is a fantastic tool to make presentations, either teaching in a classroom or making a presentation to a technical audience, some of whom will want to reproduce the results. Okay, so that's R Markdown. I'm going to show you the R Markdown code in a minute, but now let's just run through this example. So this is the introduction to R and R Markdown using the advertising data that I kind of showed in the presentation. So before the lecture, I sent out not only the R code, but also a CSV file, which contains a matrix of data. And in R, this is the line for you to read a CSV file. And you could take a look at the first 10 rows of the data. And you could tell what data it is, what type of data this is. And when you load that into R, it becomes a data frame. You can also check the different data types for each column of the data. This is rather important when you do any kind of predictive analytics task. You don't take for granted that the data is always loaded correctly. And actually 90% of the time you don't. Okay, there is something going wrong when you're loading the data into the file, and when you load the data into R. Visualizing the data, this is exactly the same plot you saw in the PowerPoint. So just a quick scatter plot to see if there's any pattern that's worthwhile for analyzing. For example, just based on this picture, you might think that TV, the advertisement budget that you put onto TV is more closely related to sales than the other two. Problem statement is basically a list of questions that you might want to get answers for after you finish the analysis. I find this part kind of important. If you don't ask the right question, then you're not going to get any kind of useful answer, certainly not any kind of useful analysis. Linear regression model, there's nothing new to describe here. I was told that everybody has at least some background in linear regression. All I'm showing you is once you finish the fit, you might want to put the line of best fit into the picture and see whether that makes sense. For example, in the last picture, yeah, there is a line of best fit, but it doesn't seem to be fitting anything at all, right? So yeah, linear regression is a good model, but a model is a model. It's a simplification of reality, sometimes oversimplifying the reality too much. And so I leave you to read the rest. And I also at the end leave on some hands-on activity so that I bring everybody up to speed. Okay, so I did a survey before the lecture and see some of you may not have seen R or RStudio, let alone R Markdown. So now let me try to share my R file or RStudio screen. So once you successfully install R and RStudio, this is the typical screen and typical layout that you will see. You have an editor screen where you could edit your script, and then you have the console at the bottom here where you actually run your code. Things on the right, you would get more experience with it than you know what they really are. Okay, so this is Ready L1 Lecture 1.rmd. RMD means R Markdown. I sent out this R Markdown file. So if you get R and RStudio installed correctly and open this file, this exact screen should be what you see. Okay? In order to produce the HTML file that I just showed you, you click on this little down arrow here and then knit to HTML. And it will pop up under the viewer. And this is precisely the file it's generated. Okay, so this is the step to run the file that I sent out. Sometimes I use R Markdown. I give R Markdown to students and then for them to do assignments. So when I ask students to send in assignment in PDF, there is an option to knit to PDF, which is quite clean as well. And then there's also the option of knitting to Word. So both of these options are quite useful as well. So I just want to introduce R Markdown to everyone. And this is actually a very, very efficient way of communicating technical contents to a wide range of audiences. And with that, let me get back to my presentation for the last couple of minutes. Just a quick summary about what we have done today. Okay, I start the study of different data science by several FinTech applications. Okay, so hopefully those applications stuck in your mind, and hopefully some of you get to learn the new types of business, the new kind of opportunity that are as a result of predictive analytics and big data. Yes, they make a huge difference in finance and in insurance. So basic definitions and basic categories and subcategories of machine learning and statistical learning. I introduced also 4 different themes in machine learning and statistical learning. One of those themes will be the focus for the rest of this lecture series. And then I just finished illustrating the usage of R, RStudio, and R Markdown. And I just want to say one last word. All of these are very useful whether you are a student or you are a lecturer, instructor, or whether you're presenting this to your boss and executives. Finally, acknowledgement about where I get all these materials and pictures from in order to make this slide set possible. With that, I will close my presentation and start addressing questions that you may have.
Yeah, it's quite many questions in the slido.com.
Yeah.
You might can answer. Yeah.
Okay, let me take a look. It's here.
Yeah.
I can see on the screen. How do we do in order to? So let me just read through the question. How do we do in order to protect our privacy when others are always targeting our data? That's a fantastic question. I'm not sure whether I have the answer for. Something that you could do on a personal level, and I constantly do, is read user agreement. Okay. I'm not sure how many of you do. I don't do it every single time, but when there are things that are kind of important, for example, when I install an app on my cell phone, I think the latest update in Apple makes it much easier to see what kind of data is being collected. And you could say no to that. And also, another thing that you could do is to keep asking. Okay? When the bank, or I just recently purchased life insurance, and the and the agent has tons of questions for me. He asks for my social insurance numbers, age, and anything else. And every single time he asks something from me, I would ask, what is this data being used? Who are you submitting this data to? So most of the time I know the answer, and sometimes I get surprising answer. For example, I used to think my agent works for the insurance company, but later I found out, no, the agent has his own company, and then the company has other business as well. So by asking where the data is going from, where the data is going, and then where it's stored, at least you get a sense of where it's going and where it's being used. Whether you could stop that from happening, that's a different level, right? Either you don't like the answer and then you change to a different agent, or you just accept and then agree to their usage. So that's a long, whiny answer, probably not necessarily answering the question, but that's small things you could do to at least stop people taking your data for granted. You could try to understand where the data is going. Next one. Nowadays, people always using historical data to predict anything. How can we know if our data is still credible to make a prediction? Brilliant. That's a brilliant question. In my mind, in my right mindset, no, I would be very, very skeptical to use historical data to predict anything. But the problem is, what's the alternative, right? So as I sometimes brand myself as a statistician, so let me just put my statistician hat on. Statistical analysis has to analyze data. Data comes from somewhere, and most of the time, if not always, data comes from the past. Okay, so we always use the historical data to predict things in the future, and I think the right way of asking this question is, what kind of tools do we have to actually extract information in the past data that's relevant for the future. I can give you a counter example. I don't believe past stock data has any relevance to predict future stock prices. Okay? So that's a counter example I have. And it's important to not abuse our power to be able to analyze the data. Meaning, yeah, I know tons of analytical tools. That doesn't mean I should throw all these tools into any data that I see. Some of the data are just useless. And being able to identify what data is actually useless is an important skill for data scientists. Can you give us example of extrapolating within the scope of data? Sure. Actuarial science, when you are trying to predict the age of people, the prediction is usually quite accurate in an average sense. Okay, so nowadays there is pretty mature algorithm or steps or process to take into account the past data, how long had people lived in the past, and then how quickly the technology, specifically in medicine and healthcare, is advancing over the years. So people are living longer and longer, but not so long that you extrapolate over 120 years or something. So within the matter of next generation, the next 5 to 10 years prediction, yeah, you could safely extrapolate the number of deaths in a particular country or in a particular region or for a particular subpopulation, like the people with pre-existing condition, people with diabetes, or just people at their age of 30, how many of them will live through their 40s. So I think those are reasonable extrapolation within the scope of the predictive power of the data. Are we going to study general additive model trees in this workshop? No, not that I have planned. I just didn't have enough time to go through the detail. I might put in a computing example if you want, but going through the details about what tree model is and how general additive model fit into the tree context, that's a little too much. I could probably do that using all the 3 lectures that I have left, but I want to give you more, give you the flavor of more topics and different topics. Can you give comments on parametric and non-parametric model related to good predictors? Another brilliant question. It depends on a lot of things. In particular, the amount, the quantity and quality of the data that you have. So one of my research expertise is in Monte Carlo simulation, and I constantly use statistical tools to analyze simulated data, and I could control, or control in quotes, control the quality and quantity of data. And in my experience, if you have a huge amount of data and you trust the data being high quality and you're not extrapolating too much, my personal preference is non-parametric. Okay? If you have high faith in your data and you believe your data could predict reasonably well for the task that you're working on, non-parametric model give entire trust to the data and let data tell the story, because you're not using a model to restrain or to simplify or to get rid of any kind of information in the data. But that being said, the ability to simplify and abstract useful information from the data using parametric model is important. Sometimes the data is so huge that non-parametric models just doesn't work at all, right? If you're in one of those domain or one of those scenarios, then it doesn't seem like you have a choice. You have to find a reasonable parametric model to summarize your data in order to make predictions. Is it okay to employ the interpolation when we need more data or smoother data? Note, data distribution does not change. Your note is actually quite important for the question you're asking here. So when you have a set of data, how can you be so confident that your data distribution does not change? I don't mean the data set that you have at hand, but in a hypothetical mind experiment, if you were to collect this data again, are you so certain that your data distribution does not change? If the answer is yes, then probably interpolation or smoothing both would work. But if you are not certain about the data distribution, then you got to be a little bit skeptical about interpolating. I lost that. Can we combine supervised and unsupervised learning together to solve a problem? Definitely, definitely. Let's see how the fourth lecture unfolds. I will show you one example. It's one of my previous research paper about how you can combine unsupervised and supervised learning in one application. Yeah, definitely. And I would go so far as saying many of the applications that I've seen would use both in different stages of solving a problem. In real cases, existing data often do not meet the assumption of a method of analysis. How to solve this? Great. There's no single right answer to the question, but it's fantastic that you realize that is a problem. Okay, so my take on this is it's kind of related to whether you use parametric or non-parametric model. So my take on this is always know the assumptions of the model you're using. Okay, so for instance, most of you have seen linear regressions. Are you able to explain clearly, both mathematically and intuitively, what are the assumptions of a linear regression model, right? So the assumptions in and of themselves tells you the limitation. So having done so many statistical analysis, I find it incredibly important to constantly visit all the assumptions, whether it's implicit or explicit assumptions that you make on the data. When those assumptions are violated, it's not the end of the world. Most of the time, your analysis is still valid, right? Some of those assumptions are purely technical to make the mathematical proof work. So when some of the assumptions are incorrect or violated, you will have to do some validation work. I will explain validation in a third lecture. You will have some validation and to check whether your predictions still have predictive power. Okay? At the end of the day, when you develop predictive analytic model, you just want to see whether there is predictive power. If there is predictive power, if your model is working well and the assumptions are violated, document them. It's not the end of the world. You can still use the model to make prediction because it has predictive power. Okay. Is it good if we determine the method first, then look for the appropriate data? No. No, that's a terrible idea. And the way you're describing it sounds like you have two tasks and you're trying to determine the order of it. And that is not a good way of thinking about how to solve practical problems. Those two steps, if you only have those two steps, then they should be in a cycle. Okay? So you might start with a particular method, look for appropriate data, and see what the analysis looks like at the end, whether it has predictive power or not. And if not, you might want to say, well, now I have a ton of data at hand with certain characteristics. Does it make sense to adjust, modify, or change the method that you're using? Okay, then once you change the method, then chances are you might want to do some changes to your data again. So the analysis actually go into cycles rather than just a linear two-step thing, right? So your question really is not which order is correct. What I would suggest is you actually change the picture in your mind and make these two items in a cyclic pattern. And that's how you continuously improve your analysis. Could you explain about reinforcement learning? Is that an AI or any real-time analysis can be considered a reinforcement learning? The question is a little vague, but I could explain what I understand reinforcement learning is. So reinforcement learning is by and large inspired by how you teach a kid, a small kid. So a kid kind of knows nothing at the beginning, start playing around, walking around, and maybe crying on things they shouldn't cry on. And then as adults, so we are the kind of the data set that fit into a machine learning algorithm, which is the kid, by providing rewards and / or penalty to a particular action of the algorithm, of the training process. So if the learning algorithm takes a particular step and receive a penalty, the next time this algorithm visit the same scenario, it would try to avoid taking the same action. And to your question about whether, if I understand the question correctly, whether reinforcement learning can be used in time series analysis, the answer is yes, and I have seen studies on those topics, but I'm not sure whether that's really your question or I misunderstood the question. In your opinion, will actuarial workflow change because of the presence of big data? Well, yeah, it's not a question of whether will or not, it has already happened, right? So if you look at a high level of things, I think during the opening remarks that InTech had a new team on big data and predictive analytics for, was it 5 years or 10 years? The company of InTech has existed for over 100 years. So the presence of big data has changed the corporate structure a new team has built, and probably the influence of that team has expanded over the years. Then yeah, the presence of big data not only changed the workflow of an actuary, it changed the whole corporate structure of how an insurance company works. Yes, definitely. Is there any more question?
Yeah, the last.
I don't see any more questions.
Yeah, it's already all the question answered already.
I don't see any more left. Or is there any that I'm not seeing?
Yeah, you answered all the question already.
Okay.
Yeah. Okay. I think that's the okay. We almost
Yeah, we are a little over time.
Yeah, a little bit of maybe yeah 20 minutes more than the schedule, and I think thank you Pak.Ben, and big applause for
My
Pak.Ben for
pleasure.
facilitating our first session of this short course, and very informative at the moment. And this is the foundation for the whole entire workshop. And for your information, Bapak Ibu, from the 3 questions, question 1 and question 2, the answer is about 50-50. And for the question number 3, we distributed yesterday. And what is it? Maybe I can share. So that's why we can see the context for all the participants before we close. Yeah, this is the question 1 and question 2, and this is the question 3. I think the last session will be the heavier for everyone, because
each of these questions corresponds to lecture number 1. So lecture number 1, I show how to knit a file. Lecture number 2 on 2 days from now will be on logistic regression to solve classification problems. And then it's now seems half of the class haven't used that before, so I would kind of adjust how to teach the second lecture, and lecture number 3 will be on validation methods. Lecture number 4, depending on how the first 3 lecture unfolds, I will adjust what topic that would be on.
Okay, thank you for the clarification. And I think we will continue the system of question and answer, so everyone will be focused on the presentation rather than there are pops up about the question and answer and everything. So that's why we separate between question and answer and the presentation, so everyone including Pak.Ben can focus on the presentation and the discussion. That's all for today, and thank you again Pak.Ben for the facilitating this session, and Bapak Ibu terima kasih. I saw the number still up there, 96 participants still active, and also Pak.Ben, thank you for still with us until at the end of the session. I know for Pak.Ben and Pak.Ben it's already 11 o'clock in the evening. Thank you. And let's close this session with the big applause for everyone, especially Pak.Ben. Thank you, and see you next Friday at the same
for the coming Friday.
At 9. Okay, thank you, and Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you.